This video is the first video in Chapter 10 comparing to populations or groups, and this one is Section 10.1 comparing to proportions. So what are we actually talking about? So suppose we want to compare the proportions of individuals with a certain characteristic in population 1 and population 2. Let's call these parameters of interest P1 and P2. The ideal strategy is to take a separate random sample from each population and to compare the sample proportions P hat 1 and P hat 2 with the characteristic. What if we want to compare the effectiveness of treatment 1 and treatment 2 in a completely randomized experiment? This time the parameters P1 and P2 that we want to compare are the true proportions of successful outcomes for each treatment. We use the proportions of successes in the two treatment groups P1 hat and P2 hat, or P hat 1, P hat 2, to make the comparison. Here's the table that summarizes these two situations. So the sampling distribution of P hat 1 and P hat, or minus P hat 2, you're going to choose a simple random sample of size N1 from population 1 with the proportion of successes P1 and an independent simple random sample of size N2 from population 2 with a proportion of successes P2. The shape for that will be when N1 times P1, N1 times 1 minus P1, N2 times P2, and N2 times 1 minus P2 are all at least 10. The sampling distribution for P hat 1 minus P hat 2 is approximately normal. You may recognize this stuff or something similar to it from Chapter 7. In Chapter 7, when we were talking about the shape, we said that we wanted to have N times P greater than or equal to 10, and we wanted to have N times 1 minus P greater than or equal to 10 as well, in order to say that the shape was approximately normal. The center, the mean of the sampling distribution is P1 minus P2. That is, the difference in the sample proportions is an unbiased estimator of the difference in the population proportions. So when we talked about center in Chapter 7, we did the mean times P hat, and that gave us what P was equal to. The spread, the standard deviation of the sampling distribution of P hat 1 minus P hat 2 is the square root of P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. Whenever we were talking about spread in Chapter 7, yours looked like the square root of P times 1 minus P over N if the sample is no more than 10% of the population. And so that also holds true for the sampling distribution of P hat 1 minus P hat 2. So check your understanding. Your teacher brings 2 bags of colored goldfish to class. She tells you that bag 1 has 25% red crackers and bag 2 has 35% red crackers. Each bag contains more than 500 crackers. Using a paper cup, your teacher takes a simple random sample of 50 crackers from bag 1 and a separate simple random sample of 40 crackers from bag 2. Let P hat 1 minus P hat 2 be the difference in the sample proportions of red crackers. So number 1, I ask us, what is the shape of the sampling distribution of P hat 1 minus P hat 2 and why? So for number 1, what you need to do is you need to go through and check all of those different conditions for the shape. So you would do N1 times P1 greater than or equal to 10, N1 times 1 minus P1 greater than or equal to 10, N2 times P2 greater than or equal to 10, and N2 times 1 minus P2 greater than or equal to 10. So for this problem, we should probably know what P1 and P2 and N1 and N2 are. So your N1 is going to come from your first sample. And so your first sample is from bag 1, and it told you that your teacher took 50 crackers from bag 1. It told you that in bag 1, that 25% of the crackers are red. So that means that your P1 is going to be 0.25. Bag 2 is going to be N2 with 40 crackers, and P2 with 35% red crackers, so 0.35. And so basically then, all I need to do to check the shape is to plug those in where they should go in each one of these situations. So I'd have 50 times 0.25 greater than or equal to 10. So that would give me 12.5 greater than or equal to 10, so that one holds. All right, here I would do 50 times 1 minus 0.25 greater than or equal to 10. So that would be 50 times 0.75. And whenever I do that, I get 37.5 greater than or equal to 10. For N2, I'm going to use the 40 and the 0.35 now, so I'm going to say 40 times 0.35 greater than or equal to 10. So that gives me 14. And then 40 times 1 minus 0.35, which would give me 40 times 0.65, and that would give me 26 greater than or equal to 10. So because each one of these held, then we would say, thus, p hat 1 minus p hat 2 is approximately normal. So number 2 asks us to find the mean and the standard deviation of the sampling distribution and to show your work. So for this one, for mean, I'm going to start by doing P1 minus P2. So I know that P1 is 0.25 and P2 is 0.35, which gives me a mean of negative 0.10. To get the standard deviation, I'm going to do the square root. P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. So I'm going to have the square root 0.25 times 0.75 over 50 plus 0.35 times 0.65 over 40. When you work all of that out, you should get 0.097. Three asks us to find the probability that p hat 1 minus p hat 2 is less than or equal to negative 0.02. So what that's going to look like is this. So whenever I'm doing that, I can do this two ways. I can either get my z, look at my table and find what p-value goes with that, or I could do normal CDF on the calculator. So just to show you what it would look like if you did the z, you would do basically this. So your x here would be the negative 0.02 that came from your problem. The mu, of course, would be what you got up here, so the negative 0.10, and you would divide it by 0.097 that you got here. Whenever you do that, that would give you 0.82. So then you would look on the table for 0.82. Whenever you do that, you would see that you got 0.7939. You could also do this on the calculator, by going to second vars, normal CDF. Your lower bound would be negative infinity. Your upper bound would be that negative 0.02 that they gave you in the problem. Your mean was negative 0.10, and then your standard deviation was 0.097. And so that gives you 0.7952, which is pretty close to where we got with the 0.7939 by looking at the table. Number 4 says, based on your answer to question 3, would you be surprised if the difference in the proportion of red crackers in the two samples was p hat 1 minus p hat 2 equals negative 0.02? So what we would basically do is interpret what this value here meant. And so for that, we would say no, we would not be surprised if the difference in the proportion of red crackers in the two samples was p hat 1 minus p hat 2 equals negative 0.02, because 79% have a difference less than negative 0.02. So that's basically just saying, what does this value that you calculated in number 3 mean? So next we're going to move on to a two-sample Z interval for a difference between two proportions. So when a random, normal, and independent conditions are met, an approximate level C confidence interval for P1 minus P2 is P hat 1 minus P hat 2 plus or minus Z star times the square root of P hat 1 minus, or times 1 minus P hat 1 over N1 plus P hat 2 times 1 minus P hat 2 over N2, where Z star is the critical value for the standard normal curve with area C between negative Z star and positive Z star. So you would check random, so the data are produced by a random sample of size N1 from population 1 and a random sample size of N2 from population 2, or by two groups of size N1 and size N2 in a randomized experiment.
Tyler Hudson, please come to the main office. Tyler Hudson, please come to the main office.
So normal, the counts of successes and failures in each sample or group would be N1 times P hat 1, N1 times 1 minus P hat 1, N2 times P hat 2, and N2 times 1 minus P hat 2, and they're all at least 10. Independent, both the samples or groups themselves and the individual observations in each sample or group are independent. When sampling without replacement, check the two populations are at least 10 times as large as the corresponding samples, and that would be what we call the 10% condition. So check your understanding. Are teens or adults more likely to go online daily? So the Pew Internet and American Life Project asked a random sample of 800 teens and a separate random sample of 2,253 adults how often they use the Internet. In these two samples, 63% of teens and 68% of adults said they go online every day. Construct and interpret a 90% confidence interval for P1 minus P2. So for this one, this is going to be our 4-step process. So we're going to start with our state. So for state, we're going to say we want to find 90% confidence interval for P1 minus P2. Our plan for that would be to check random. And so in our problem, it states random. The next thing we could do is check independent. So that's basically the 10% condition. So is N1 less than or equal to 1/10 of population in N1? And is N2 less than or equal to 1/10 of the population in N2? So our N1 we know is 800. That's our sample size for teens, less than or equal to 1/10 of the entire population of teens. So basically to do that, we would just times this by 10, times this by 10, and we would say 8,000 less than or equal to N1. So basically, does it make sense that we're taking a sample of 800? Do we have at least 8,000 teens that we are talking about? And so, of course, we have at least 8,000 teens in the world. So now we would move on to N2. So in N2, we have 2253 less than or equal to 1/10 of N2. Do this one the same way, so multiply by 10 on both sides to get rid of that fraction. Whenever you do that, you would get 22,530 less than or equal to N2. So do we have a sample of at least 22,500, or do we have at least 22,530 people that we had before we took this sample? Of course we did. So now let's move on to normal. So when we talk about normal, we're going to look at that N1 times P1 greater than or equal to 10. N1 times 1 minus P1 greater than or equal to 10. N2 times P2 greater than or equal to 10. And N2 times 1 minus P2 greater than or equal to 10. So that would look like 800 times 0.63, because we were taking 800 teens and saying that 63% of them went online every day. So when you do that, it's 504 greater than or equal to 10. Here you would do 800 times 1 minus 0.63, which would be 0.37. Whenever you do that, you get 296 greater than or equal to 10. For N2, you were taking a sample of 2,253 adults, and you were saying that 68% of them went online daily. So when you do that, you get 1,532 greater than or equal to 10. So then for N2 times 1 minus P2, you'd have 2,253 times 0.32 greater than or equal to 10. That would give you 721 greater than or equal to 10. So we would say, thus, approximately normal. So then for the do step, our p hat 1 we would need to say is 0.63. Our N1, of course, would be 800. Our P2, or our p hat 2 would be 0.68, and our N2 would be 2,253. So to do our confidence interval, we would need to use that formula from the last slide. Ooh. So basically, we would end up with 0.63 minus 0.68 plus or minus. Our Z star for this would have to do with a 90% confidence interval, which is going to be 1.64. Whenever you work all of that out, you would get a lower bound of negative 0.0823 and an upper bound of negative 0.0177. And so our last step, of course, is to conclude. So we would say we are 90% confident that the actual difference in proportions of teens versus adults who go online daily is between negative 8.23% and negative 1.77%. Two-sample z-test for the difference between two populations. So suppose the random, normal, and independent conditions are met to test the hypothesis, null hypothesis where n1 minus n, let me start over. Suppose the random, normal, and independent conditions are met to test the hypothesis, the null hypothesis where p1 minus p2 is equal to 0. First find the pooled proportion p hat c of the successes in both the samples combined. Then compute the z-statistic using this formula here. Find the p-value by calculating the probability of getting a z-statistic of this large or larger in the direction of the specified by the alternative hypothesis. So a one-tail or a two-tail. Conditions that you need to do. So when you use this test when you have random, so the data are produced by a random sample of size n1 from population 1 and a random sample size of n2 from population 2, or by two groups of size n1 and size n2 in a randomized experiment. Normal, so the counts of successes and failures in each sample or group is n1 times p hat 1, n1 times 1 minus p hat 1, n2 times p hat 2, and n2 times 1 minus p hat 2, and they're all at least 10, and independent, so both the samples or groups themselves and the individual observations in each sample or group are independent. When sampling without replacement, check the two populations are at least 10 times as large as the corresponding samples, and so that would be your 10% condition. So check your understanding on this one. To study the long-term effects of preschool programs for poor children, researchers designed an experiment. They recruited 123 children who had never attended preschool from low-income families in Michigan. Researchers randomly assigned 62 of the children to attend preschool, paid for by the study budget, and the other 61 to serve as a control group who would not go to the preschool. One response variable of interest was the need for social services as adults. In the past 10 years, 38 children in the preschool group and 49 in the control group have needed social services. So your control group would be those who did not go to preschool. So number 1 says, does the study provide convincing evidence that the preschool reduces the later need for social services? Carry out an appropriate test to help answer this question. So for number 1, we're going to state P2 is the proportion attending preschool who need social services later. P1 is the proportion not attending preschool who need social services later. So our null hypothesis would be P1 minus P2, and so that would be 0. What that basically would mean is that going to preschool has no effect, so that's where the 0 comes in. So remember, you're taking the difference of these two, so you're basically saying that it doesn't matter whether you get a preschool or don't get a preschool. The alternative hypothesis is P1 minus P2 is greater than, just greater than 0. So basically, what that means is that you're wanting to show attending preschool has an effect. And so basically, you're trying to prove the alternative hypothesis and reject the null hypothesis. All right, so for your plan, you got to check random. So it tells us that it was randomly, the groups were randomly chosen. You got to check independent, which means you got to do that 10% condition. So is n 1 less than or equal to 1/10 of the entire population? Is n2 less than or equal to 1/10 of that entire population? So for n1, you were taking 61 students and not sending them to preschool. 61 serve as the control group who would not go to preschool. So we just want to make sure that we think that there are at least 610 students or preschool age students in Michigan who do not go to preschool. N2 was 62. So I get 62 from here. So that would mean that there would need to be 620 in Michigan that did go. So it would be independent if at least 620 poor kids attend preschool and 610 poor kids don't attend preschool. So next I need to check normal. So that's a 4-step process. N1 times P1 greater than or equal to 10. N1 times 1 minus P1 greater than or equal to 10. N2 times P2 greater than or equal to 10. And N2 times 1 minus P2 greater than or equal to 10. All right, so your N1 is 61. Your P1 is going to be your proportion of those who actually needed social services. So that comes from up here. Of course, those would cancel, so you'd have 49 greater than or equal to 10. Here you would have 61 times 1 minus 49 over 61. So that would be 61 times 12 over 61, which is going to give you 12. For N2, you would use 62. Your proportion that needed social services would be 38 out of 62. So that would turn into 62 times 24 over 62. Those would cancel. 24 is greater than or equal to 10. So because all of those were met, then we would say thus it's approximately normal. So then your do step would be to calculate your Z. This formula came from the other side. Let's see, so your P hat 1 would be equal to 49 out of 61, which turns into 0.8032. And your P hat 2 would be equal to 38 out of 62, which gives you 0.6129. And your P hat C is going to be your total people that needed social services. So that would be 49 plus 38 out of 61 plus 62. And so that gives you 87 out of 123, which turns out to be 0.7073. So basically you would take all of those and you would plug all of those in, and I'm rushing through this because you guys are standing outside the door and looking in this window at me, being real creepy. So whenever you do that, you would end up with your Z at 2.32. So you would look for this on your table, and whenever you did that, you would find that your P was 0.9898. So then your probability that P1 minus P2 is greater than 0, which was your alternative hypothesis way up there, would be 1 minus 0.9898, which would be 0.0102. So then your conclude step would be, since your p-value 0.0102 is less than your significance level, so we're going to let it be 0.05, the sample is statistically significant at the 5% level. Thus, we reject the null hypothesis and assume preschool reduces the need for social services. Remind me to show you that on the calculator as well.